This being thermodynamics, and thermodynamics dealing with thermal equilibrium almost always, we have a section of the course that's non-equilibrium thermodynamics. So that would be flow, either heat flow or material flow where you're not at equilibrium. But most of the other situations, we're either at equilibrium, or even in those cases, we're trying to strive towards equilibrium. So not being at equilibrium is what drives a battery to give you voltage. Okay, so it's trying to get to equilibrium. So what is equilibrium? This morning we're going to talk about the Boltzmann distribution and how it defines what we mean by thermal equilibrium. And so last time we talked about probability, and this is an extension of that. So the probability of a particle being in a particular energy level is given by this equation. And maybe you see that e to the x term, e to the minus energy over kT, that's that Boltzmann factor. That's that Boltzmann piece that he developed in 1877 in looking at the equilibrium of gas particles and their velocities. And he was able to use this mathematics to describe the pressure, volume, equilibrium velocities for a gas. It was interesting too, in order to solve that problem, he said, let's assume for simplicity's sake that we have a countable number of velocities, that the gas particles had discrete velocities, that they couldn't have any, it wasn't a continuous function, it was a counting function like this with a summation. And he said, we don't actually believe this, or I'm not making a claim that nature is, these velocities come in discrete values, but it simplifies the math. What's funny about that is years later, when Max Planck was trying to solve the black body radiation problem, he used this same equation based upon discrete energy values. And he knew what was happening. He was like, if I use this equation, I'm using quantized energy levels. I'm using discrete energy values. And that was a mathematical shortcut for Boltzmann, but Planck saw that this might solve the UV catastrophe, that black body radiation problem, and it did. So the Planck distribution law solved the radiation distribution of a black body, and it was based upon discrete mathematics. So that was interesting. So really, I'd call Boltzmann the father of quantum mechanics, even though Planck and de Broglie and Schrodinger and Einstein get credit for it. Really, it started with Boltzmann. So this Boltzmann equilibrium function will tell us the probability of being in any energy level. And so this morning for the Boltzmann distribution problems, we'll just do a two-level system, and then we'll start looking at translation, rotation, and vibrational motion for molecules. And so this Boltzmann constant K, you've seen this before, it's 1.38 times 10 to the minus 23rd joules per Kelvin. Now, a lot of times we don't have our energy level diagram, or the energy spacing between two levels is not in joules, it's in wave numbers. And so it's helpful to convert that to wave numbers. And so if you take that Boltzmann's constant divided by Planck's constant and the speed of light, you can convert it from joules per Kelvin to wave numbers per Kelvin. And so this is a really nice clean number. It's 0.695 wave numbers per Kelvin. Now what do we mean by this Boltzmann's constant? It looks like a conversion factor, and that's one way to think of it. So you give me a change in temperature of 1 Kelvin, and I can tell you how much energy has changed in the system. It's gone up by 1.3 times 10 to the negative 23rd joules for 1 degree change in Kelvin, or 0.695 wave numbers for 1 degree Kelvin. So if you change the system 1 degree Kelvin, you've changed the energy of that system by Boltzmann's constant, 0.695 wave numbers. Notice in the denominator of this exponential we have kT. So that kT essentially is turning that temperature into an energy. And so we have energy on top and energy on bottom. So we're just looking at the energy available in the system, that's the temperature. We convert that temperature into energy, and then we look at the quantized energy levels and say, how do they compare? So the denominator in this exponent is kind of like what I call the thermal bath. It's how high the temperature is of the system. And then we compare those energy levels to see if they're below water in that bath or above water. Are they below that available temperature or above it? If they're below that available temperature, then they're going to have quite a bit of energy. They're going to be molecules in that energy level. If they're way far above the available energy, then they're probably not going to be excited. And statistically, though, some of them will be, and we'll see that. So that's the Boltzmann factor. Now, if you wanted to figure out all of the all of the possible events, then you would sum over all energy levels. And that's what's going on in the denominator. So we're taking the Boltzmann factor for each energy level in a quantized system. And some of those may be degenerate, right? Like a p orbital is degeneracy of 3, a d orbital 5, f orbital 7. You would put that degeneracy in here for g. And so if we were doing orbitals that were degenerate or energy levels that were degenerate, then we would use that g to keep track of the degeneracy. You see how, you would have just the same energy term for all 3 of those p orbitals. And so you could calculate the Boltzmann factor 3 times, or you could just multiply that one by 3. So it's just taking into account the degenerate energy levels. And then you sum all of those up, and that's that normalization factor. Remember last time in the probability chapter, we talked about rolling a dice, and there were 6 outcomes. So the denominator was 6. You had a deck of cards, there were 52 possibilities, and so the denominator was 52. That's all this is the normalization constant in the denominator. It's the sum of all the possible outcomes. And then if you want to know about a particular outcome, that's the numerator. So the probability of being in state I is the Boltzmann factor for that state divided by all of the possibilities. So it's straight probability, what we covered last time. And so that degeneracy is G, energy is epsilon I, and the temperature is Kelvin. Any questions on this? Notice I say note card bait, definitely, having that available, because whenever you're doing wave numbers, you don't want to have to constantly put in Planck's constant and the speed of light. The more you can reduce the times you have to use exponential notation in your calculator, the fewer errors you're going to make. Okay, times 10 to the minus 34, times 10 to the 10th, or what have you. You're going to mess those up on average. The number of operations you have to punch in your calculator, what's the mean time between failures, right? Can you punch 100 keys perfectly? Well, if you have to punch 101, you're going to make a mistake. So that denominator, the probability distribution, is called the partition function. So it has a name in statistical thermodynamics. It's not the normalization constant, although that's what it does. We call that the partition function. And so then you can just break that denominator out. So we call it Q, lowercase q. And it's the sum of all those Boltzmann factors. I've left the degeneracy out of this one, but it could go in there as well. So it's just the sum of all the possible energy states. Now I'm using beta because some of the books use beta. Some of the books have 1 over kT. And so I include both. So beta is just 1 over kT. That's just, and kT is beta to the minus 1. I always wanted my daughter to get that on a ball cap because her name's Katie. Beta to the minus 1. She never went for it. What can I say? I thought it would be great. And so then the probability of any particular configuration is that Boltzmann factor on top divided by Q. So anytime you're doing these calculations, the first thing you calculate is Q because you're going to need that going forward. And so the partition function calculations, we'll see a whole bunch. We'll have a translational partition function, a rotational partition function, a vibrational partition function, electronic. We might even have other kinds. We'll have them at high temperatures, at low temperatures, and so on. So there'll be a lot of discussion about this partition function going over the next couple of weeks. And so this, pretty interesting, this simple result satisfies all of those previous constraints. This is how you find out the probability of being excited. And you can calculate this. When would this be useful? Well, it's very useful in NMR because whenever you have the spin states, say you have a proton in a molecule, there's no energy difference in the molecular Hamiltonian. Whether the nucleus is spin up or spin down has no bearing on the energy of the molecule. But if you put it in a magnetic field, it does. And so that spin of the nucleus can be with or against the magnetic field. Now, what do you think is the lowest energy one? You ever played with magnets? With. Yeah, so actually it's against. So like magnets, you put them with and they'll flip. Yeah, so the lowest energy is if the magnetic field is going up, then all the little protons with their spins going down, they're paired, spin paired with the magnetic field, but some of them are unpaired, and so those will be slightly higher in energy. Well, how far apart in energy depends on the magnetic field, right? If you've got a really strong magnet, it's going to take a lot of energy to unpair them. And so there'll be an energy difference based upon the strength of that magnetic field. And your signal depends upon there being a difference in population. So if you drive these energy levels far apart with a strong magnetic field, you get more signal because the probability of being in the ground state is higher than the probability of being in the upper state. If these energy levels are really close together, then there's really no difference in probability. So you could calculate the probability of being in the excited state versus the ground state based upon the partition function and the Boltzmann distribution if you knew the energy differences as a function of that magnetic field. And you could see how much more sensitive our 300 megahertz machine is versus our 60 megahertz machine. Because you could figure out what the magnetic field is in each of those. So let's just look at some of the features of this Boltzmann distribution law. We talked about microstates, meaning different possible arrangements of the nuclei. Like think about all of your proton spins, you know, these two are up and those two are down, and all of these possible microstates. We will assume that those occur with equal probability, and yet the dominant configuration is the one with the highest probability. So it's very unlikely that all of those nuclei will be spin up, although that is a possibility, but there's only one possibility of those. Think about if there's 6 protons, 3 and 3. All of the possibilities are 3 up and 3 down. The first one could be up, second up, third up, then down, 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 but then you could have first up, second down, up, down, down, and all of the different places you could put 3 and 3. That's going to be the dominant configuration because it has the most possibilities. So the scrambled result is the dominant configuration. The isotopically pure, or all the spins being up, or like flipping coins 4 heads in a row, that's a possibility, but it's unlikely. It's more likely to have 2 up and 2 down, or 1 up and 3 down, or 3 up and 1 down. All of these scrambled results appear to be the dominant configuration, and that's what would be the one that emerges as our equilibrium possibility. The adjacent configurations are insignificantly different than the dominant configuration. So if you think about flipping a coin 50 times, right? It's the most probable that you would have 25 heads and 25 tails in some arrangement, right? You think about all the possibilities, heads first, tails second, and so on. You could have 25 heads, 25 tails in some random order. That would be the most probable. But having 26 and 24 is not that different. And so this takes that into account too. You could calculate the probabilities for all of these different outcomes. And so the adjacent, when we say the adjacent configurations of microstates are insignificantly different than the dominant configuration, you're going to have some variability in that result. The macroscopic properties of the system, let's now think about these 50 coin flips, and instead of you having to flip them individually, let's just take them and set those quarters on the table and look at them, and hey, flip themselves, heads and tails. Some flip to heads, some flip to tails, some stay put for a little while and then flip. And if you're looking at those and you take a snapshot and add up all the heads and tails, it's going to be pretty close to 25-25. There'll be some 24, 26s, some 23, 27s, but observations of the macroscopic properties of the system will appear to be unchanged. And that's what we mean by equilibrium. What do we say always, even going back to freshman chemistry? At equilibrium, does the system stop changing? What's going on at equilibrium? Use the language we talk about in freshman chemistry. Yes. Yes, the reactants to products and products to reactants, the rates of conversion come to be the same. And so that's what we're talking about here. Observation of the macroscopic properties, the amount of products and reactants seem to be unchanged. But that's just because the rates going forward and backward have come to equal each other. Okay, when you have no products, then the forward rate is fast and the reverse rate is slow. But as the products build up, then their reverse rate starts to increase. And so then at equilibrium, it doesn't appear that the system's changing, but it really is. And then this unchanging dominant configuration is what we call the equilibrium state. And it's described by the Boltzmann distribution law. So we could apply this to reactants and products, and we will. We will actually derive the equilibrium constant using Boltzmann distribution. So in the end, we've solved, statistical thermodynamics has solved chemical equilibrium. That's pretty amazing. We can do it mathematically. We just don't have computers big enough. We know the math. And so we can solve all of the equilibrium problems that we know of, but we just don't have computers big enough to put the full system in there. Think about trying to keep track of a mole of molecules. At this point, we don't have the hardware. So let's talk about some problems. Let's do these problems with and without degeneracy. So can you see up there at the top, maybe a little small, we've got the Boltzmann factor for a two-level system, and we've got the energy set at essentially the energy spacing where it matches kT. So this will be e to the kT over kT, or e to the -1. And so that partition function here is going to be, it's a two-level system, so it only has two terms in the sum. And so we have the ground state here, e to the 0 over kT, and then e to the -kT over kT, because we've set this energy level as equal to our thermal energy. And so this will be the partition function, 1.368. Okay, it's a unitless quantity, because the units in the exponent cancel, and degeneracy is just a counting. So it's just a counting number. It's not, doesn't have units. And so that's one thing to note, put in your notes. The partition functions are unitless. So if you're calculating a partition function and you end up with units, something's wrong. Okay. So you always check that. The units are a good guide. And so then we can do the probabilities. So the probability of the system on the left to being in the ground state, state 0, is just going to be that individual Boltzmann factor here divided by the partition function. And so that's going to be 0.73. So 73% chance of the molecules or this system being in the ground state for this two-level system. And you can simply do, since it's a two-level system, 1 minus that to get the other one. But to show the math, we have the Boltzmann factor, this piece here for the excited state, divided by the sum of all of the states. And so that's 0.27. So 27% chance of being in the excited state. So that's a classic two-level system Boltzmann distribution. So that would be, if you had 100 molecules or particles thrown into this system, 73 of them would be in the ground state, 27 would be in the excited state. Now that's not significantly different than 74 and 26. Or 72 and 28, okay? So those are going to be almost equally probable. But you're not going to have, 80 in the ground state and 20 in the excited state. That's pretty far off from equilibrium. When would you make the decision that the system's not at equilibrium? I don't know. It'd be a judgment call. But, if you had 100% in the ground state and 0 in the excited state, and you had this kind of temperature where the temperature gave you enough energy to be excited and they weren't, there'd be something fishy. You'd definitely not be at equilibrium. Also, notice you don't have a population inversion, so you couldn't make a laser out of this system. So thermal equilibrium sets up where the ground state has the most molecules if there's no degeneracy. If you have degeneracy, you can get a population inversion. You can have more molecules in the excited state, but not in a system without degeneracy. Now let's add in degeneracy. So here we have in system 2, we've got two states. The upper state is doubly degenerate. And so then that just changes this Boltzmann factor piece with the 2 right there. So now our partition function has increased. This is important. Let's think about what the partition function tells us. Notice it's a Boltzmann factor and it's for every energy level. So we go through the whole system and find all the energy levels, and we calculate essentially a relative probability for being in each of those levels. I say relative in this case because we haven't yet normalized those factors. But yet, if you just take the Boltzmann factor for any two levels and divide them, you've got the relative probabilities between those two levels. So we go through and we calculate the Boltzmann factors for all of these, and we add them up. And that sum is essentially a count of the number of energy levels that are populated. So go ahead and write that down. The partition function is like a count of all the levels that are populated. So notice the first one, the first partition function is 1.3. It's greater than 1, and that's telling us that there's more than one energy level that's populated. Okay, notice the second one is 1.7. It's higher, so that just means more energy levels are populated. And so this partition function goes up as temperature goes up because more energy levels are populated. What if I take this temperature all the way down to 0? What's that? Yeah, everything goes to the ground state because the ground state energy is 0. And so and we'll look at that. I think it's its own slide. So we'll talk about that as it goes to 0. But Q goes to 1. If the ground state's not degenerate, Q goes to 1. If the ground state's degenerate, it goes to whatever the degeneracy is. Because you're taking that e to the 0, which is 1, and multiplying it by its degeneracy. And that's the only term in your partition function. So your partition function goes to 1 as temperature, as you cool everything down. And what is that partition telling you? It's the number of energy levels that are populated. And so if you had a doubly degenerate ground state, it'd be 2, because 2 levels are populated. If you had a triply degenerate, it'd be 3. Yeah. Notice this is interesting. We take the degeneracy into account, and now we have a 21% chance of being in each one of these energy levels, or a total of 42% chance of being in the excited state. We haven't changed the temperature at all, and yet now there's fewer molecules in the ground state. This is a weird result. Temperature is the same, the energy difference is the same, we just have more chairs in the excited state. And just the fact, like musical chairs, if there's a chair there, someone's going to sit in it. Okay? And so if you add degeneracy, you add a chance for molecules to go there. And so this is just an interesting fact of nature, that adding degeneracy can cause excitation. In fact, it'll raise the energy of the system. If we add up the energies now, because we have more molecules in the excited state, the energy increases with degeneracy, and we haven't changed the temperature at all. That's weird. Okay. So if that, like, you're like, how can the energy change if the temperature hasn't changed, right? That's a weird result. But that's one of these quantum weirdnesses, okay? And it occurs when you're down in where you can observe the quantum effects. That's one of the quantum effects, that the expected energy is going to change depending upon degeneracy and the structure of the energy levels. Okay, so let's look at very high temperatures. So think about that factor, e to the minus energy over kT. So kT is in the denominator of the exponent, and if temperature gets really, really high, then that fraction gets really, really small. And essentially it goes to e to the minus 0. So at super high temperature, that Boltzmann factor for the excited state goes to 1, or if there's degeneracy, it goes to the degeneracy. But notice here, so I've got the ground state one here, that's e to the minus 0, because the energy is 0, and it's the energy in the numerator of that fraction. So e to the 0 is 1. But then at high temperature's right there, it's in the denominator of that fraction. So if temperature goes up, that fraction goes to 0, and we have e to the minus 0, which is 1. So I have 1 plus 1, or a partition function of 2. So at high temperature, what does my partition function go to? It goes to 2, which tells me there's 2 energy levels that are populated, and I have a 2-level system, so everything's populated. Okay. And it should be a 50-50 mix of the probabilities. because the factor for the top level is 1, the factor for the bottom level is 1, the partition function is 2, so I have a half and a half as far as my probabilities. Does this make sense? Yeah, because you got enough thermal temperature, it doesn't matter to the molecule if it's in the excited state or the ground state, because there's really, compared to the temperature that molecule has, it is irrelevant whether it's in the excited state or the ground state. And that's the mental idea I want you to have right now, is to say, if I've got a high enough temperature, the energy spacing is irrelevant. Make sense? Yeah. Same thing on the right. If I go to a high temperature with degeneracy, it's irrelevant whether it's excited or ground state, whether it's in one or the other degenerate states. And so it's 33, 33, 33. There's got 34 in there somewhere. Okay, so it adds up to 100. But it's irrelevant because I have enough temperature that I can be any one of those states, and there's not a problem. Okay. So at high temperature, we go to what's called equipartition. Big word for the course. It's made up of 2 parts. Equi, which is the piece that stands for equal, and partition means dividing the molecules among the different energy levels. So we have equal division of molecules among all the available energy levels. And later we'll have partition functions using the equipartition theorem. And so you'll know, oh, okay, that's what we're talking about, equipartition of all of the available energy levels. And it's a really easy result. So we go through some stat mech that looks really ugly, and then because we typically work at high temperatures, everything's so easy. It's just like 3/2 RT. Boltzmann, the gas constant times the temperature, and you've got it. You know, so it's super easy in the end. But I want to go through the translation, rotation, and vibration just to show you what you can do for a particular molecule and what Gaussian's doing for us when Gaussian calculates these things. Okay. So let's take a Kahoot real quick. And then there's practice problems after this where I go through a Boltzmann problem by hand very slowly. And it's on YouTube. And it's this lecture from last year, but it starts at 12:48 when I go through the pen. So you can see when I go through all of this pen work right here. So my voiceover for going through all of that is on YouTube, and so it'll walk you through a 2-level system by hand. And so I want you to go through that. Because we've kind of missed today, I want to play catch up and do the translation today. So let's do this Kahoot. Yes?
So when we were on the last slide, when we had system 2 with the degeneracy, and we had 67% in the excited state, is that when we get the population inversion for laser action?
It is a population inversion, but it's also the equilibrium result. And so I actually don't know if that would laze. Yeah. So it might, but you're also going to have those, again, it's the equilibrium condition, so I'm not sure if it would laze. Most of the time we drive it with the pump photons and really get it way out of equilibrium. And so, but it was a good question. I really don't know. It is a population inversion, so it looks like you could get lasing action, but it would create a non-equilibrium situation. So as those molecules would drop to the ground state, they'd immediately find their way back to the excited state. So I don't know. Be something to research. What's that?
Maybe they lace on the way to equilibrium.
Yeah.
Past that 50%.
Yeah.
You've got 17% of the time it's lacing.
Yeah. Yeah. I know, this is what is that, 7 digits? Dang. Oh, I hit start, nobody's in, so hopefully I didn't take it. Yes?
Do lab cert this week?
No. We're going to start with everybody else this semester.
Okay.
So we'll have a couple So I'll adjust the lab schedule. Tanner and I need to get things straightened out. Is that ever right? No. 7, 8? I think that's it. Okay, let's go. Can you read that? Very cold temperature or systems without degeneracy. So either one would work on that. Somebody's holding out. Good. I'd like to see that. Okay, so what is the denominator of the Boltzmann distribution law called? Is it just kind of to reinforce what I just told you? Yay, I'll have to see that. I need to take a picture of that. Screenshot. That wouldn't be a perfect score. Partition function goes to blank as temperature goes to 0 Kelvin. So without degeneracy. Okay, pretty even split here. Remember, it's the count of energy levels, and so we have to have some energy level populated. So it'll go to 1. So everything goes to the ground state, and then we just have one energy level populated. So it's, again, it's a partition function. That name means how I partition my atoms and molecules and electrons. So I partition them all into one spot. So it will go to 1 as temperature goes to 0 Kelvin. And then the partition function serves as a statistical blank. Yay! Oh, so great. All right, so let's do the, let's see, podium. It really, yay. I don't have all these memorized, so I don't know who's who, but don't say because of the video. Yay, it's just kind of like Mario Kart. I love that part. Okay, let's move on. I gotta get this to get it to quit. So now let's do the translation. The translational partition function. It's pretty short. It's like a mini lecture. There's a couple of work problems in here that you can do if we don't get to them. And so we've talked about the partition function, the denominator in that Boltzmann distribution. It's just some review here. Again, we want to know the probability of being in a particular energy level divided by the number of total possible outcomes. And then in terms of the molecular partition function, we have translation, rotation, and vibrational motion. And then also a partition function for the electrons. But the electrons are not thermally excited, so that one's really simple. It could be really complex, but because the energy level spacing in electrons are so high, we really don't have any thermal effects to speak of. So let's think about the probabilities in a two-level system. We calculated that for a single temperature last time. Here I've got a system. This is slightly different than you have in your notes. If you look at the two-level diagram in the notes, if you printed those off, it says 0 and 2 kT at the top. But I went ahead and moved that to wave numbers at room temperature. So room temperature is about 200 wave numbers. And so this is sort of twice that, 400 wave numbers for our energy level spacing. And then these are the probabilities. If you look at the bottom, the temperature of the system in terms of units of kT, so 1 kT, 2 kT, 3 kT. So 2 kT, if we're at room temperature, is about 400 wave numbers. And so if we increase that temperature above room temperature, so essentially this is room temperature at 1 kT, then we're moving up to 10. And the green is the excited state probability. And notice that at 0 Kelvin, the probability of being in the excited state is 0. Okay? And so our population goes to 1, and the blue is the partition function, and it goes to 1. And then the red curve is the ground state probability, so the probability of being in the ground state. So at 0 Kelvin, it's a sure thing to be in the ground state, probability of 1. Now as you start to raise the temperature, so here at kT equals 1, we're at room temperature, and we've got about half the energy we need to be excited, but yet there's already some probability of being in the excited state. And we've already lost some molecules from the ground state. So that's the probability of being in the ground state, and it's less than 1. It's maybe like 80% chance. Okay. So even at half the amount of temperature we have needed to get to that excited state, we already have 20% of the molecules in that excited state. Again, it's just statistics. They're going to try to occupy everywhere they can at a given temperature. And so they do get above the thermal temperature a surprising amount. But as you really increase the temperature, what does it converge to? It converges to the 50% mark, right? Where you have equal probability of being in the excited and the ground states. And that partition function in a two-level system will approach 2. So that's our two-level system plotted as a function of temperature. Notice that this is just what I just said, that approaches the 50-50 mark at high temperatures. There's some probability even at low temperatures of being excited, but it drops out at 0 when you get close to 0. So let's talk now about a particle in a one-dimensional box. We spent a whole semester talking about that in the fall, and so we're very familiar with the energy level equation. And so here we have this partition function that is the sum of all of the Boltzmann factors. And the Boltzmann factors have the energy levels in them. And so now instead of epsilon I, we'll just call it epsilon n, meaning it's the energy of the quantum state n for a particle in a box. And so we can put that particle in a box energy equation in there. N squared, h squared over 8ml squared. And then we can sum over all of those. Well, it's an infinite sum, right? Because we have an infinite number of quantum numbers. We start with n equals 1 and go up to n equals 2, 3, 4, and sum all of those up. But it's basically a function of temperature. How high do I have to sum? Okay. Well, it turns out that molecules are pretty heavy. We spoke about an electron in a box, and it was a tiny little box, 7 angstroms. Okay. It's kind of a rare case. I mean, most of the time we're dealing with atoms, which are, even a hydrogen atom is 1,000 times heavier than an electron. So that mass is in the denominator, so those energy levels are really close together. And then we have a box that's bigger than 7 angstroms, and that's in the denominator. And so the energy levels are even closer together. So the difference between n equals 2 and n equals 3 is insignificant. The difference between n equals 50 and n equals 60 is insignificant. So we can turn this summation into an integral, because the change from n1 to n2 to n3 is so small that it's infinitesimal. And so we can integrate over n, the quantum numbers, and then we took beta and broke it out, and now it's 1 over kT. And so we can integrate this equation with respect to n and see what we get. And we get this equation here. So this is the partition function for a particle in a one-dimensional box. We'll do 3 dimensions in a second. Straightforward. The L comes out, and they have all of this mess. So let's look at this. What are these things? H is Planck's constant still. Okay. KT is KT, and then this M is not meters. That's mass. Okay, so that's the mass of the particle. It was an energy equation up here. Mass. Okay. And so we have this, and it's a kind of a weird thing. It's raised to the 1/2 power times L. Okay.
And so then we end up with this, they looked at this and said, this looks like the thermal wavelength. It looks like the Broglie relationship. I don't see it, but that's what they say, you know. And so it's the length of the box divided by lambda, capital lambda, and this capital lambda is called the thermal wavelength. Okay, because if you look at those units in that partition function piece, that gives you a distance. So this has a unit of length, and so that's why they're calling it a wavelength. Now, you might think of it as saying, well, if we got the size of the box down to the thermal wavelength, then I'm starting to see quantum effects, right? But as long as the box is bigger than my thermal wavelength, then I don't see the quantum effects. Okay, and so that's one way you can think of this thermal wavelength. Okay. If we did this in 3 dimensions, it just is pretty cool. The partition functions are always multiplied by each other. So we have L in the X direction, L in the Y direction, L in the Z direction, and you have this front piece multiplied 3 times, and so it's cubed. And so we have this weird piece out front raised to the 3/2 power, okay, and times the length in X, Y, and Z. Well, length in X, Y, and Z gives you volume. And so then we have this volume over lambda cubed is our partition function. Now, volume, we may not want to use volume. We may want to use pressure, okay? Because again, you don't necessarily want to know like if I wanted to calculate the volume of this room, yes, I could get out a ruler and so on. Or I could just say, how many moles of gas do you think I have in here? And what's the pressure and the gas constant, nRT over P. So I could just take out the volume and put nRT over P, and then I've got the partition function as a function of the amount of molecules I have, the pressure, and the temperature. And so then we end up with this partition function. And this is unitless. This is a really ugly equation in terms of all the different units. And so because you know the partition function is unitless, that's how you know whether you use atmospheres or pascals, whether you use grams per mole or kilograms, right? So whenever you're doing these problems, 90% of it is the units. And so you have to use as a guide the fact that the partition function is unitless to know if you got the units right. Okay? And if you have the gas constant, which is joules per mole Kelvin, and you want to know where that mole is going to go, you know, you've got moles out front, moles of particles out front, so if you do it for 1 mole, then that mole's gone. Okay, so sometimes you end up with, you've got a per mole in there. And you say, well, just for 1 mole of this, so it's that per mole times 1 mole, the moles are now gone, and it's unitless, and so you've got it calculated for 1 mole of gas. So this is one of the ugliest ones, because you've got Planck's constant cubed. Okay, that's 10 to the minus 34 times 3, so 10 to the minus 90, so 72, 10 to the minus 72 in there. Crazy numbers. Boltzmann's constant to the 3/2 power, temperature to the 5/2 power. These are the weirdest exponents you've seen in a while, okay? And so just, it is what it is. Don't let that stress you out, it's just the equation, okay? And so you should be now, you know, comfortable with really, really ugly equations, and this one's really not ugly, it's just the exponents are unusual. Okay. You want to see an ugly equation, look at the log normal distribution. Okay, so the practice problems here are pretty straightforward, but I put them in there just so that you can see the numbers and see the units cancel. So here it is for the thermal wavelength for argon at 1 atmosphere at room temperature. And so I calculate the thermal wavelength. So what's the thermal wavelength of argon? 1.6 times 10 to the minus 11 meters. And so I'd have to put it in a volume that had a dimension of 10 to the minus 11 meters for the quantum effects of argon to start to show up. Okay, which makes sense. You know, an atom, you know, an angstrom is 10 to the minus 10 meters. So I'd have to squeeze it down to the atomic scale for its quantum effects to show up, and that makes sense, doesn't it? You'd have to have an atomic scale box for you to see the quantum effects. You've got argon in a big room like this, you are not going to see the quantum effects. okay? How many energy levels are, in translational energy levels, are populated for argon at room temperature in 1 atmosphere? Think about the partition function. It tells us the number of energy levels that are populated at a given temperature. It's just like an estimate. Right here, partition function. We calculated it 5 times 10 to the 30. Yeah, so that's how many energy levels are populated in translational motion for a mole of argon, atoms. Now you might say, wait a minute, a mole of argon atoms is only 10 to the 23rd atoms. How can I have 10 to the 30? So that's what I'm saying. It's an estimate of the number of energy levels that are populated. But it's telling you there's a lot. Translational motion, there's a lot of excitation in translational motion. Okay, I'll leave the second problem to you. This is kind of fun. So you've got partition function at a temperature, and I ask you the partition function at a different temperature, but you don't know the mass. And so you've got to take into account that 5/2 temperature dependence. So these are all in the notes. So with that, we're done.